just want to talk about what you made for the last one, because I knew last time I missed everything you said for. Okay, it is working. We are recording. That's good. So we finished example 6, just to kind of point out some of the things in the boxes that weren't donuts, that are still very important. The general limit theorem, if the limit from the left equals the limit from the right, they both exist, it's a finite value, then the general limit exists and vice versa. If the limit from the left or the limit from the right are not equal to each other, or either one of them fails to exist, the general limit does not exist, okay? And remember, these are the only two times where the limit is going to exist at a point. If the function is continuous, like on part 2, or up above, like part 1, either the function value is not defined, or it is, but it's somewhere else, right? That's what we defined as the whole. So the limit is what y'all just found. It's the y value of the whole, not the y value of the function. All right, and then the other thing was the definition of continuity, the 3-step definition, okay? The road coming in has to equal the function value, which is the bridge, which has to equal the road going out, which is the limit from the right. So road, bridge, road, limit, function value, limit. They all have to exist and equal each other, the same y value. If any one of those 3s fails to exist, or any 2 of them do not equal each other, it's game over for continuity, and we cite that reason, okay, based on the definition. So let's go ahead and now define, since we have the terminology, we will define then what it means to be a removable point discontinuity, also known as a what? Whole, right. So that is a term that you could use. You could use the word whole, just know that it's a removable point discontinuity. So first of all, let me tell you what makes it removable. So let's say we have something like this at x equals c. Removable means that whether or not the function is defined, it's not the point there. If I gave you a little manhole cover that is a point, could you put it down anywhere at x equals c and make that continuous? Yes, you could put it down right there at the limit value, and you make it continuous. So that's what makes it removable. You can redefine the function at x equals c to make it continuous. All right, so here's the definition. If for some function f at some x value c, if the general limit as x goes to c equals L, so again, L is some finite y value, and remember, if the general limit exists, that means the roads are lining up. From the left and right, the two one-sided limits are approaching the same y value. But either one of these two things happens. Either the function value is undefined, that would look something like this. There actually is no dot anywhere. Or the function value does exist, but it's not equal to the limit value. Maybe it's up here somewhere, right? Or down below somewhere. In either of those two cases, we say that we have a removable point discontinuity or a hole at the coordinate c comma L. And so notice the y value of the discontinuity is the limit value. It's not the function value, which would be this if it exists, right? It's the y value of the hole, okay? And that y value is exactly what you would then need to redefine it to be to make it continuous, which is, again, why it's called removable. So let's look at example 7. It's a wonderful type of function for teachers because, in this case, I get a 2 for 1 out of it. We call those types what? Yeah, piecewise. Piecewise. We define the function in pieces, okay? So whenever you have a piecewise function, the first thing you want to do is just look at the pieces and see where they're defined. So this looks like it's a quadratic parabola everywhere to the left of 2, and a slanted line with a slope of 2 everywhere to the right of 2. So it's part parabola, part slanted line, and they change at x equals 2, okay? Now it says here to algebraically determine the following. We haven't sketched a piecewise function in a while, so I'm actually going to take the liberty and break the rules and show you how to sketch it, because it might have been a while since you've sketched a piecewise function. Anyone sketch a piecewise function over the summer? No, I didn't either. So let's do it together. All right, so here's how you sketch a piecewise function. Give yourself some axes, x and y. And again, what's the most important x value here? 2. So just kind of come off the y-axis and call that 2. You don't have to actually put tick marks for everything. Yeah, you could do line snaps now to make your lines pretty too. I forgot about that. All right, so here's what we know about x squared. He comes in and he bounces at the origin and then he continues on. But we're not going to draw him past 2. It would be really nice to know the y value, though, that the parabola stops at when it gets to 2, yeah? So the way we figure that out is we just plug it in. What's 2 squared? 4. So I'm going to come up here and call that 4. Now I want to put something down at the point 2, 4 to show that's where the parabola ends. But can I put a solid dot? No, because the way it's defined, it says strictly to the left of 2. So instead, as a marker, I'm going to put in open circle. Okay? Now from there, I'm going to use my knowledge of what the parent function x squared looks like just to kind of complete it. Okay? And I'll use maybe a different flavor here. It's going to come down and bounce, and then by symmetry, it's going to look like that. So you should try to make it pass through the mirrored point -2, 4. All right? And that's as accurate as you have to be. All right, now I want to know where the line picks up. So, hey, it'd be nice to know the y value where the line assumes at 2. So once again, by direct substitution, what do you get when you plug your 2 in there? 3. So I'm going to come right below there and call that 3. And once again, I got to put an open circle. Okay, because it's just greater than 2. If that were greater than or equal to 2, I could put a solid dot. And then from there, you can either pick another point to the right or just realize it's a slope of +2. So if you just draw it going up like that, that's fine. Okay, so there's the piecewise function. That's how you draw it. Okay, so now if you have the graph, whether you generate it yourself or maybe it's something that's given to you, answering questions about this function at 2, very, very easy thing to do. Let's do it. F of 2, is that talking about the roads or the bridge? The bridge, the function value is the bridge. So that's like what we've been doing all along. We have to evaluate the function by going to the piece where it's defined at 2. Which piece, top or bottom or neither, is defined at 2? Neither, right? That's why when we sketched the graph, we never had a solid dot anywhere at 2. It's explicitly not defined at 2. Only to the left and right of 2. So f of 2 equals what? Does not exist. It's non-existent. So going back to that 3-step definition, does this function have a chance at being continuous at 2? No, it's game over, and that's the reason you would cite, since f of 2 is not equal or equals d and e. Okay, so the next question, what would be the limit as x approaches 2 from the left of 2? Okay, well, that's pretty fun now because since we have the graph, we can pretend like we're driving on it, right? So hop on the graph to the left of 2 and start driving towards 2. Yeah, we're getting closer to 4. Okay, we're getting closer and closer to the hole whose y value is 4, right? And the limit as x approaches then 2 from the right-hand side, hop on the graph somewhere just to the right of 2 and start driving back towards it. You're getting closer and closer to the other hole, which has a y value of 3, okay? So again, notice that the limits from either side can exist independently of the function value. So if the limit from the left is 4 and the limit from the right is 3, part D, what can be said, if anything, about the general limit at 2? Does not exist. Yeah, that goes back to the general limit theorem, which, if you remember it up here, said that the general limit at C will only exist if the two one-sided limits are exactly the same finite value. And last time I checked, although they're close, 4 and 3 are not the same. Okay? And so let's go ahead and finish off the argument then. What can be said about the continuity of the function at 2? It says to justify. That means use the 3-step definition. So in a complete sentence, we'll say something like f is, or is not, I forgot. Not, good, not continuous. And you can abbreviate that for now, C-O-N-T. And then you say add x equals 2. You're specifying where. And that usually gets a check for answering it correctly. And then here comes the justification, since. And then I'm just going to, there's several different reasons we can cite. So the first one could be what I said on part A, right? That could be one of the reasons. So you could say either since f of 2 equals d and e. That would be fine. Or, number 2, what else could you say? 4 does not equal 3. Very good. 4 does not equal 3. The left side and right side limits are different. So either one of those. You don't need both. Just pick one and go with it. Okay, so now the question is there a way to answer those questions without drawing the graph first? Because that's kind of labor intensive. Yeah, we know how to calculate f of 2. For f of 2, we look for the equal sign. Yeah, that's the equal sign in the equation. Okay, there was no equal sign at 2, so it was d and e. So if we're trying to evaluate the limit from the left of 2, How did we get 4? Plugged into the first one because it was the left side of 2. So left of 2 is always less than 2. They have the same la sound. Okay? Left of is less than, which also looks like an L, which helps you remember which one is which, right? Less than. Left of is less than. Sweet. Okay? And then if you want to figure out what the limit is from the right-hand side of 2, right of 2 is greater than 2. Okay? Greater than 2. So let's write that here. Right of 2, or just right of anything, is greater than, which you can remember that by doing this. Okay, yeah. Greater than. All right? So there we go. From a piecewise function, we have road, bridge, road, but now we have like less than, equals to, and greater than. So you can kind of come back up here and add that if you want for a piecewise function. The road coming in is going to be the less than piece, the bridge is going to be the equal piece, and the road on the right going out is the greater than piece. We'll have a lot of piecewise functions. Okay? Less than, left of, at is equals, right of is greater than. So you can compute them algebraically, okay? Now, here's the thing. Without having the graph, is there a way to determine what the graph looks like based upon this information without sketching it? Yeah. If you're coming in from one side to a 4 and the other side to a 3, regardless of whether the function value exists, what type of discontinuity do you think that is? That's a jump, right? We call that a jump. Okay? We don't say it's like 2-hole graph. There are 2 open circles there. We call it a jump because the y values physically jump from one finite value to another finite value. Okay? That's a jump discontinuity. Do you think a jump is removable or non-removable? Non-removable. And here's why. The function's not defined there, but let's say we did redefine it. If I gave you a manhole cover, can you put that manhole cover down anywhere at 2 and make that continuous again? No, you put it at the top, that doesn't work. Put it at the bottom, it doesn't work. Put it down here, you're way off. Put it in the middle, no, it still doesn't work. Okay? So it's a non-removable. You can't fix a jump and make it continuous. The only discontinuity you can fix is the removable point, okay, or the hole. So let's go ahead and define it now. A non-removable jump discontinuity, or you can just refer to it as a jump, says the following. If for some function f of x, again at some arbitrary value, x equals c, if the limit from the left of that x value is, we'll call it L sub 1. L sub 1 is just some finite y value. Okay, not infinity. And the limit from the right of that x value is L sub 2, another finite y value, where, of course, L1 and L2 are not the same, okay, where they're different. And this is important. Regardless of f of c, it doesn't really matter where the function value is. The function value could be either like nowhere here, or it could fill the top hole, or it could fill the bottom hole, or it could be, you know, somewhere way down here. Because it never fixes the jump, it doesn't really matter what the function value is. If that happens, then you have a non-removable jump. And this is important. We don't list it as an ordered pair. We just list the x value where it occurs. All right? So here you wouldn't say that there's a jump at x equals 2, 3, and 2, 4. You would just say at x equals 2. Yeah. Okay? It's the vertical location. So it works in reverse. If you know there's a non-removable jump at x equals c, then you know the 2 y values from both sides are going to finite values, but different values. The roads are not lining up, okay? And that's exactly how it looks like in the real world. This is an undoctored photograph of something. I don't know if it's an undoctored photograph, but that's the consequence in the real world, right? Do those guys look too concerned? No, they don't look too concerned. In fact, they look like they're daring each other to leap across it, right? And that could be very dangerous, right? Like this guy tries. Yeah. Okay. So this guy says, okay, I need a running start. Falls down. Okay, I'll run over here. Run, and then he missed. All right, this guy runs, makes it. There's only one guy left. Okay, and he's not smart, so he just goes to save his friend. All right, see, the point being, I don't know, he falls down. The point being, it's not very safe, right? Nor desirable in the real world in this scenario, okay? They're not going to fix that. They have to break it and rebuild it, okay? Anyway, let's look at example 8 then. What?
Are the rows like shifted sideways, or is one higher than the other?
Oh yeah, we don't really get that perspective. Who knows? It could be a jump on several different planes, right? Yeah, right. That's when one contractor doesn't communicate with the other contractor. Maybe this is what happened when the two railroads met and they tried to drive the Golden Spike. And they're right? It takes a little bit of communication. All right. Let's look at example 8. Using the definition of continuity at a point. I remember that. That was up here, Oak Ridge Road. Okay? Using that, discuss the continuity, of the following function, justify. All right, good thing it said to use the 3-point. Otherwise, when it says discuss, you might like turn to a friend and start chatting away, right? Or write an essay. That's not what it means. It means we need to determine where and where not this function is continuous. So, first thing you do when you see a piecewise function is resist the urge to panic, right? Think of it as like not a 3-headed monster, but maybe something less terrifying than a monster. Maybe more cute, like a 3-headed baby, right? Right? Little baby, 3-headed baby, right? It is part what at the top? Graph? Line, slanted line, mx plus b, right? And then it changes to a parabola, 1/2 x squared at -2. And then at 2, it changes from parabola to a horizontal line, right? If you have a constant over an interval, it's a horizontal line. So it goes from slanted line to parabola to horizontal line. And the two most important x values, based on the definition, are -2 and 2. Do we have to check those values for continuity? Yeah. Think of it as a relay race. Anytime one graph is changing into another graph, we need to check to see if they're exchanging at the same y value. Because if they're not, or if it's not defined there, there's going to be a discontinuity. So every time there's a switch, you need to check that x value. But the other thing you want to look at are the pieces themselves. Do those functions have any built-in discontinuities of their own, like vertical asymptotes or something? Lines, parabolas, and horizontal lines? No. No, they're all polynomials, so they're continuous everywhere. Something that would have a built-in discontinuity, if you wanted an example, would be something like looking at the graph of 1 over x for all x less than 1, right? Because 1 over x has a vertical asymptote where? At 0, right? Which is to the left of 1. So that would be another discontinuity that's built in. But we don't have to worry about that here. So it appears then that the only two places where this function may not be continuous are at what? -2 and 2. So let's go ahead and do our analysis using the 3-step definition. Now, because we're doing two different things, you want to get in the habit of communicating clearly. So over here to the left, I'm going to go ahead and say at x equals -2. You're just kind of explaining what you're doing over here. Now, if you want, you can go ahead and set up your math notation, okay, your road, bridge, road. And it would look something like this. Let me move to the middle here. The limit as x goes to -2 from the left of f of x, that's your road coming in, f of -2, that's your road going out, and then the limit as x goes to -2 from the right-hand side, the road coming in from the right or going out on the right. Okay, so what that does is it just forces you to bank your points for the notation. And now all you have to do is collect those data points and compare them. If any one of those two exist but are not the same, it's game over. If any one of those doesn't exist, it's game over. Okay? So let's go ahead and compute those now without sketching the graph. The limit as x goes to -2 from the left. -2 from the left. Which piece? Top, bottom, or middle? The top, right? Remember, left of is less than. So right there, by direct substitution, we get 0. Yeah. Now, we don't care if it's a solid dot or an open circle at this point. If you were to graph it, it would be an open circle, but the limit doesn't care what happens at -2. That's this guy's job, f of -2. So which piece is actually defined at -2? The second one. Okay, so for that, you're looking for this equal sign right there. So now we're going to use that one. We plug it in. -2 squared is 4. 4 halves is 2. So at this point, Do we even need to see what the third one is? No, we don't, okay? 0 doesn't equal 2, it's game over. So having said that now, just to be thorough, let's see what it is. I'm kind of curious. I'll use a different flavor, though, red. The limit from the right of -2. Which piece do we use for the right of -2? Greater than. Yeah, which is which piece? The bottom is greater than 2. That's way too far to the right of -2. The middle one, yeah. It's a compound inequality, so you want to make sure when you go to the right of -2, you're going just to the right and not too far away. So the way that you read a compound inequality is from the inside out. X is greater than or equal to -2, and X is less than or equal to +2. Okay, because this is pointing that way, and remember the alligator eats the bigger thing. That's X is greater than -2. So it's still the middle piece. Now, if you notice right away, because it was less than or equal to, you can then say, it's the same company that's building the road on the right and the bridge. It's the same company, so they're going to get it right. Whereas the less than, that's a different company, okay? So for what it's worth, that's also 2. So if you want to be thorough, or maybe I just ask you to give me each of those 3. But here's your argument now. You want to answer it and then justify. F of X is not continuous, not in France, but at X equals -2, comma, that would get a check, since, and the easiest way would be what? 0 does not equal 2, yeah. Again, this is the last day for this crummy projector screen, because I'll install the good one over the weekend. All right, yeah. Y'all should sign y'all's name on it at the end of class. Y'all are the last ones to use it. You got me through the first week, crummy projection screen. We'll miss you. Not really. Okay. So here's what I want y'all to do. There's only one other X value. X equals 2. Go ahead and do your own analysis now and determine whether it is or it isn't. Answer it the same way. Statement with the justification. Middle piece and the bottom piece. Right. Less than is left limit equal is function value, greater than is right-sided limit. So you're just plugging in. Try to copy the notation though that we just did for -2, but do it for +2. Don't forget to put f of x in there. Yeah. When you're writing your limit, it's real easy to forget f of x in front of the limit. Okay. That'll cost you a point eventually. The x approaches goes beneath the limit, and the f of x goes in front of the limit, and then equals. So establish good habits from the very beginning. Yeah, it switched at -2 and it switched at 2, so that's why we had to test them. If there was another one and it went like to 4 and switched to 4, we would have to test 4. Yeah, that's where those numbers come from. One more you'd have to put equals 2, because we need all 3 of them to equal. So yeah, 2 equals 2 equals 2. I know it seems silly, but you're referring to all 3 of those things. All right. All right, raise your hand if you think it's not continuous. You're all correct. Well done. It is continuous. Okay, now, I'm going to show you a slightly different way. If I don't specifically ask you to evaluate all 3 of those things, you don't necessarily have to write all 3 of them down first, get them up and running, and then evaluate them, because it could be like this one here, you don't even need the third one, right? So it's just extra writing. it's fine if you do that. It develops a good habit. But I'm going to do it this way. I'm just going to write them down as I go. So I'm thinking road, bridge, road. So the road coming in from the left is the limit as x goes to 2 from the left, okay? Here's what I'm saying. Don't forget the function up there and then equals. All right, so now I'm looking at that's left of 2 and at 2, and that's greater than 2. So notice you can already tell that the left-sided limit and the function value are the same, right? Because it's less than or equal to. They're built by the same company. They're going to get them in the same place, okay? So your road coming in from the left and the bridge are going to be the same value. They both use the middle piece, so by direct sub you get 2. So that's going to be 2, and f of 2 is also going to be 2. Now, if those were different, it'd be game over. If either one of them didn't exist, it'd be game over. But because they're the same, we now need to check the third one, right? That's the road going out or coming in from the right. The limit as x goes to 2. Don't forget f of x. And now that's greater than 2. That's the bottom piece. Well, nothing to compute there. It is 2. All right? So now you use your powerful perception and determine if those are the same or different. They're the same. Okay, so what's the conclusion? Is or is not? It is. So in a complete sentence, f, you could say f or f of x, it doesn't matter. F is the name of the function. F of x is just the grand name of the function, okay? F is continuous at x equals 2, comma, that would get a check. Yes, it seems silly to say that, but you need to show that all 3 of them are equal to each other. So unless you want to write all 3 of those over again, just refer to these 2's, and we know that you're referring not to like just any number equaling itself twice, but those specific quantities that are labeled and calculated up above. And that would get your justification check, okay? The top is the answer. This line here is your justification in the presence of this right here, okay? All right, so that's the math language that you always use when you're justifying. All right, cool. So we don't really even know what the graph looks like, but we know that the only place where it's not continuous is where? -2. So make sure before you walk away from a problem that we actually answer it. We should probably make one final statement then. It says, discuss the continuity. So here we go. So is a great transitional word. And instead of, let's go ahead and say, so f of x is continuous. I'll spell it out this time. You could say for all x not equal to -2. Okay, and that would be kind of like your final statement, the thing that concludes the entire analysis up above. So it's continuous everywhere except at this one point, and if you want to know why, see my work above. Okay? All right, so that's a pretty good problem. It kind of involves everything that we've been doing so far, piecewise functions. Okay, one more problem. I think we have time. There's a fun way to do this, okay? Look at example 9. F of x is equal to that 3-headed baby again. But now we have a couple of interesting things here. We have like a dearth of numbers. It's like we're missing some things, right? We have more letters than numbers, okay? No big deal. It's telling us to find the values of a and b, so that the function is continuous at -1. Well, why is -1 so important? Oh, look. That's where it changes. It goes from a parabola to the left of -1 to, notice in this case, when x is -1, it's 4. That's actually a point, not a horizontal line. And then to the right of -1, it's a slanted line again. So it goes from a parabola to the point -1, 4 to a line. And I need to find the values of a and b so that they are connected at the point -1, 4. It's continuous, okay? Bless you. So the 3-step definition of continuity not only works to determine if something is continuous, but also to answer questions like this, okay? So let's go ahead and set up our road, bridge, road machinery. The limit as x goes to -1 from the left of f of x. Okay, left of is less than, that's the top piece. Directly substituting in for x. What do you get? Into the top piece? Less than, right, is left of. So -1 squared is 1. 1 times A is A, so we get A minus B. That's the best we can do. If we knew what A and B already were, that would be a number. We don't know what it is. That's the best we could do. So that's the road coming in from the left. The bridge is f of negative 1, and that's the middle piece. It says when x is negative 1, call it a 4. And now the road going out to the right, writing it down correctly, that's the limit as x goes to negative 1 from the right. Right of negative 1 is greater than negative 1. That's the bottom piece. So again, by direct substitution for x, we get negative 2a plus b. So if that's going to be of any help to us, we need to understand the relation among these three things to each other. They all have to what in order for the function to be continuous there? They have to be equal to each other. But if you say a minus b equals negative 2a plus b, you're going to have one equation with two unknowns. So yeah, not only do they all have to equal each other, they all have to equal 4, okay? So what you could do then is say, so, the transition word again, a minus b has to equal 4, and negative 2a plus b also has to equal 4. And now, congratulations, you set up a system of equations, linear equations, like you worked in Algebra 2, which you could solve by guess and check, elimination, augmented matrices, matrix multiplication, Kramer's rule, prayer, whatever, okay? Substitution usually works pretty well, okay? Remember, that means you solve either one of these for either variable, and then you plug them into the second. So that works nicely. But in this case, I'm going to do elimination. I'm going to add them together, because remember, the idea in elimination is you get one of the variables to go away. And I already noticed that the coefficients of the b's are opposites. See that? So it's ready to go. If you just add vertically then, a minus 2a is negative a. Negative b plus b is 0, so it goes away. 4 plus 4 is 8. So if negative a is positive 8 is negative 8. And so there's one of the values. I'm going to go ahead and box it. You don't have to box it. But when you box it, you're declaring that as your answer. There's more work to do, and I don't want it to get lost in the shuffle. Okay? So now how do we find the other value? Plug it back into which one? Will the bottom one work too? Yeah, either one works. The top one looks more user-friendly. More work, you're right. So, again, a transitional word. Negative 8 minus b equals 4. And here's where you want to be careful. You don't want to lose it at the end. Okay, you can be real careless at the end and get the wrong value. However you solve linear equations, I use like a shell game. I'll bring the b over there and the 4 over here. So negative 8 minus 4 equals b. And that means b equals negative 12. Okay, and I've answered the question. So this makes a really good multiple choice type question on a test. And what I would probably have you do is I would say, like, what is the value of a plus b that makes it continuous at negative 1? Because I don't want to have to type everything, a and b. So in that case, once you find your values, in this case, you would just add them together. So that would be negative 20. Or I might have you subtract them or multiply them, okay? So it turns out, if you notice, both a and b were negative. So our parabola ended up opening what? Up or down? If a was negative. It ends up opening down, and the slope of the line, if a is negative, was also negative. So here's what we accomplished. You can start packing up. I'll just draw this picture. We made a parabola that opens down turn into a line. We made it connected. Now, if I draw it like that, even if I didn't put that dot, you could tell where it became parabola to line, because there's like a little sharp point there. But it could have been that it was a nice parabola and then it turned into a line, and you don't know exactly where it became a line from a parabola. Okay? Both of those are continuous, but the one on the right is smoothly continuous. And that's a whole different property that we're going to be studying in the next chapter. Smoothly connected, not just connected. Very important. All right, you can put your calculators away. There's about a minute left, so I'm done. Have a fantastic 3-day weekend. I'll be back in here Tuesday morning at 8 o'clock if you need any help, okay? Don't leave early, Will.